significant figures. So how you do this one is asking for the angular momentum. Which you know for a point object would be something like r cross p. But for a solid object which is spinning about its axis, so this is like rotation or orbit or something. To get the spinning one, you use I times omega. All right. Now the problem gave us omega, which is 10 radians per second. And then in addition to that, it gave us the radius of this thing. Which was 0.2 meters. And it gave us the total mass, which was 25 kilograms. All right, so how do we get the moment of inertia from these numbers? It's a solid cylinder is spinning about the axis in its center. R squared over 2, and you said mr squared, what times r squared? It's the other. It's this one. I didn't catch if that's what the first part of what you said was or not. So yes. So then what we need to get the L for spin would be 1/2 mr squared omega. So that's, let's write it down here. Half and 25 kilograms and 0.20 meters squared and 10 radians per second. All right, so now we do a little bit of quick mental math. This squared gives us 0.04 times 25 gives us 1 times 10 gives us 10 times 1/2 gives us 5. All right. Hopefully we're all warmed up now. Today we're going to do fluids. So last time you'll recall we did stress and strain and elasticity. For solids mostly, although it was applicable to fluids as well. Today we want to look at what happens with pressure inside of a fluid. If a fluid, the difference between, let's say, a liquid and a solid, one of the primary differences is that solids will resist shearing stresses. Liquids largely will not. Layers in a liquid can slide across each other. There is some resistance. It comes from the viscosity of the fluid. But that's more like a frictional resistance. That's more like the resistance that this thing has to sliding across the tabletop when I push on it. It's not that it's actually connected to the table in some meaningful way. There's just some friction that holds it in place if I push lightly and resists if I push heavily. So if a fluid, friction between layers in a fluid is called viscosity. So there is some resistance. We're going to ignore that for today. We'll come back to viscosity in 2 lectures, so Friday. What we only want to look at today is what happens when you apply a bulk stress to a fluid. And what kind of bulk stress does a fluid apply to itself or to something submerged in it? And as you'll recall from last time, bulk stress is pressure difference. All right. So how did we define stresses in general and therefore pressure in particular? Well, always a stress looks like some sort of a force per unit area. So pressure must be a force per unit area. And in particular, pressure is the force that is usually applied, though not always, but usually we think of it as a force that's being applied because something is surrounded by a fluid somehow, or has a fluid within it somehow. So if you take some object that you've placed in air, there's some pressure on this object from the air. Is that the only thing that can ever apply pressure, by the way, a fluid? No. Anytime that you push on something, you are applying some pressure to it because your hand has some actual area, there is some actual force from your hand. But we're going to consider pressure today in terms of a fluid is applying it, or maybe something is applying it to a fluid, like, say, a piston. It's force per unit area, and specifically the force in the case of pressure, especially from a fluid, the force in particular is perpendicular everywhere to the object that it's being applied to. All right? So this is always a perpendicular force relative to the area. As a simple example, consider a sphere. And now consider that you submerge the sphere in some fluid. What counts as a fluid, by the way? A liquid, but also a gas can count as a fluid. So this sphere could be just in the air, for example, or it could be underwater. The pressure on this sphere will look something like this. It's basically everywhere perpendicular to the surface of the sphere. And it's the area in question. We're going to use the surface area. And specifically, it's the surface area which is submerged in the fluid. So if you have a sphere that is like half immersed and half out of a fluid, then we use the pressure on the surface that's actually immersed in the fluid. The part that's out of the fluid, that part of the surface area doesn't count. Or maybe there's another fluid, in which case you use the pressure from the other fluid. From this, and from the fact that pressure varies with depth in a fluid, these two things, most of the rest of the section on fluids will follow. So basically what we're in right now, for what it's worth, is chapter 9, if you didn't write it down last time. This right here, I think, is introduced in section 9.1. Pretty much all the rest of the chapter up to about 9.5 or 9.6, somewhere in there, follows from this, and from the fact that pressure varies with depth. How does pressure vary with depth, by the way? How do we know that pressure varies with depth? Okay, hint. This is fluid statics. What's the condition for statics? Write it up here. What's the condition for something to be in static? Or in static equilibrium specifically? No net force. And no net torque. And the results of those two things are no changes in velocity, in other words, no acceleration, no changes in linear momentum, no changes in angular momentum, therefore no angular accelerations, etc. All right? So now let's consider a fluid. Water, for example. It's easier to do with a liquid, to do this with a liquid than with a gas, because gases are more compressible. So let's consider some fluid like a liquid, like water or mercury or alcohol or whatever, rubbing alcohol, drinking alcohol, any of that. All right, so now let's consider that you can look at some area inside the water. And it could be some, not area, but some region. It could be, for example, a spherical column of water. All right. Now, we just stated that this system is at equilibrium. So if this system is at equilibrium, then it follows that any piece of the system, any, let's say, volume of water within the system must also be at equilibrium. So if that's the case, then it follows that this particular column of water that I've drawn must have a net force on it of 0. Must be a net force of 0 on this column of water. Now, what actual forces act on the column of water? On the one hand, this column of water surely has some mass to it. So there must be a downward force from gravity, assuming, of course, that it's somewhere on the Earth, and therefore gravity is acting on, or somewhere on a planet or what have you, where there could be gravity acting. What other forces exist here? Normal force? Okay. When does a normal force exist? Important question. When do you get normal forces? There's no normal force? Okay. So to answer the previous question, when you get a normal force, well, when you have something that's pressing against a solid surface, right? So this is not pressing against any solid surfaces. It's just a bit of water that's sort of on top of a bunch of other water. There's no normal force there. There's no resistance to having one bit of water pass through another.
Buoyant force.
Okay, a buoyant force. So we could have an upward force called the buoyant force. And it turns out that you are correct. That is the other force in place. Or that's what we call the other force in place. That force must somehow be equal to the weight of this water in order for the system to be at equilibrium. And so now the next question is, where does that buoyant force come from? So where's the buoyant force coming from? Well, you have pressure from the liquid. You have pressure from that liquid on anything that's immersed in the liquid, and we can count this particular segment of the liquid as if it has been immersed in the rest of this liquid. So you have pressure down here going upward. You have pressure pointing everywhere in. This is the top of it, though. There's no pressure above. So at the end of the day, you have pressure in this way, you have pressure in this way. Those two things cancel because everywhere along the diameter they can be diametrically opposed to each other. But from below, you still have some pressure pointing upward like this. And there is no pressure above it to counter that. So your buoyant force is the difference between the pressure up here and the pressure down here. Now, one step further with that, it turns out that we don't necessarily need to have the top of this out of the water or at the surface of the liquid. This works in general. There will be some pressure difference between bottom and top, and that pressure difference will be equal to, as it turns out, the weight of this little column of water. So how much does the column of water weigh? Well, it's m times g, but that would be the same thing as r squared, that's the radius, times pi times h. So that's the volume times density times gravity. Okay, so this right here is volume. This right here is density. And in this case, I've chosen the volume to be a volume of a cylinder. It could be any shape you desire. You could make it into a cube of water or a box of water. You can make it into a sphere of water, although it's a little more difficult to show what's going on because that means that you're not just applying a pressure to a flat lower surface. You have some curvature. It still works, but you can't do it algebraically. All right, so that's why I've chosen a shape of a flat bottom to it and an equal symmetric flat top. All right, so now let's consider what we have here. We have pressure, this force per unit area. It follows that this must be equal to mg over a. So that would be r squared pi h rho g over, okay, what's the area? The area is the area of the bottom of the cylinder. Bottom of the cylinder looks like a circle. Area of a circle is r squared pi. So now we can cancel an r squared pi from top and bottom, and what we get is that the pressure at the bottom of it is rho times g times h. Density of the fluid times gravity field strength times height or depth, basically height of the column, which is also depth in the fluid. And this can be expressed as a difference in pressure, rho g delta h, for an arbitrary column that is placed at an arbitrary depth. Meaning instead of having the top right at the surface, the top is maybe here under the surface somewhere. Still works out all right. All right? So I'm going to write that over here. I'm going to erase a little bit. In fact, I'm going to erase this so I have some space to work on. But I'm going to write the relevant equation back. So the relevant equation says change in pressure for a fluid in general is the density of the fluid times the gravitational field strength, G, 9.8, or Earth anyway, 9.8 newtons per kilogram, times the change in height, or in other words, the depth within the fluid. So if we draw out our container again, we have our little plug of water here. This right here is your delta H. Okay? Now, let's go back to this buoyant force thing. If we have a pressure difference between top and bottom, it implies that there's a difference in the amount of force that's being applied to the bottom of the thing upward versus to the top of the thing downward. Okay? Other thing of note, other important point, we don't need this to be a plug of water anymore. It can be an arbitrary object that's been immersed in the fluid because we derived all of this just by considering the pressure of the water outside of this column. So if you replace this column of water with something else, say a cork, you haven't changed any properties of all the rest of the fluid that's surrounding it. Not appreciably anyway. Okay, so this means that the buoyant force remains. And that buoyant force, FB, just looks like the change in pressure from below to above times the cross-section area. Delta P times A. Now, in order to generalize this to something that's not necessarily a cylinder shape or a cube shape or whatever, but just an arbitrary shape, what can we do? Because it no longer becomes obvious what delta P is. It may be changing. If you have this sphere, for example, delta H is different here than it is here. And therefore delta P here and delta P here are going to be different. And also A, what do you use as the area here? You no longer have just a flat lower area. It can be calculated using integration, which we're not going to do for the obvious reason that we're not a physics with calculus class. All right. So how else can we obtain the buoyant force for a general, or maybe I should say a generic shaped object? And the answer is, we can consider what happens if you replaced the generic shaped object with water of the exact same volume. If you replace the generic, or whatever fluid you've put it in, I should say. If you replace the generic shaped object with the fluid that you've submersed it in of the same volume, what happens to that fluid? Does it float, sink, or just stay there? Basically, it should stay because the rest of the fluid's at equilibrium. So this fluid should also be at equilibrium. Implication, the amount of force upward from the buoyant force must be equal to the weight of that fluid. So in general, the buoyant force, FB, equals weight of fluid displaced. All right. So for something of an obvious shape or geometry, something that has an easy volume to find, in other words, you can use the density of the fluid times the volume of the object times G. That's your buoyant force. So volume of the object times density of the fluid times the gravity field strength. All right, so now let's consider a few, maybe we should say a few sundry things before we apply this. Okay, a sundry item number 1. What happens if you have more than one fluid? For example, maybe you have air, and then you have water under the air. In other words, you go to the lake or the ocean or whatever. That's basically what every major body of water on the earth is going to be like. You have air, then you have your fluid, your water. What does this do to the pressure? Well, it turns out that if you want to find the total pressure at some point, maybe I'll draw it in switch colors. Say I want to find the pressure at this point right here, P. Okay, this point is somewhere underwater. We'll call it H sub P for point, P sub P for pressure at point. And this water is underneath some other fluid like the air, which is exerting some pressure on the water at its surface. Then the total pressure at that point P is equal to the pressure from whatever's above your liquid. For example, 1 atmosphere worth of pressure, if it's air at sea level on a calm day, plus the pressure from the fluid itself at this depth. So that would be density of the fluid times free fall acceleration times the depth to that point. In other words, you have a delta P here from the fluid. That's your total pressure at that depth. Okay, item 2. What is the atmospheric pressure? You know that it's 1 atmosphere on a calm day at sea level and so on. What is the actual value, though, in SI units? Does anybody know it? This is more like, in some ways, a piece of trivia information, but it's useful to know for some of your homeworks and so on. 1 atmosphere pressure is approximately equal to 101 kilopascals, where 1 pascal, the unit of pressure, or of stress in general, is defined as 1 Newton per meter squared. All right? So it's about 101 kilopascals. Not necessarily exactly, but close. You can also go look it up in stuff like torr or pounds per square inch and so on. I think it's 14.7 pounds per square inch. I think it's like 760 torr or some such thing. But the main one that we're interested in using is pascals. So here's your 1 atmosphere. All right, so now let's have an example. All right, let's have really an example. Let's figure out what let's figure out what depth you have to go to in water before the pressure is about 1 atmosphere worth of pressure. So, what depth in water gives a total pressure of 2 atmospheres at that depth? maybe you're jumping into a pool and you got to figure out how far down you go. We're assuming, that the surface is sort of at sea level. Etc. All right. Maybe it is in fact the sea. By definition, it's at sea level. What changes, by the way, if we use the sea instead of the swimming pool? Important question. Yeah?
Like the density.
The density will change. So for fresh water, what is, maybe I'll just ask you guys what it is. What is the density of fresh water? Nobody knows what the density of fresh water is? It's just one? Just one what? Sorry? Did you say it? Oh, you said it. Gram per centimeter cube. Yeah, I was looking down when whoever it was said it. All right, good work. It is. It's grams per centimeter cubed. Now here's the thing though, we don't actually want it in grams per centimeter cubed. So this is correct, but it's not how we want it to be. We want it to be in kilograms per meter cubed. The reason being that we want to figure out in atmospheres, which this is 202,000 newtons per meter squared by definition from what a Pascal is. So what is it in kilograms per cubic meter? It's 1,000. That's right. I also didn't see who said that one, but good job, whoever you are. All right. So, and then for comparison, salt water. So this is, maybe I should use seawater. Seawater actually varies. The salinity of seawater actually varies with depth. The deeper you go, the more salt you have in it. So it depends on what you want to use. Do you want to use average salinity, in which case you'd use about 1,035 kilograms per cubic meter? Or do you want to use roughly the surface salinity, in which case you'd use 1,025? So we'll use surface. All right. So let's pick one of these two at random. We'll do the freshwater one because the numbers are rounder. All right. So what we want to know is what depth, that's another way of saying what's the value of H. Well, we have a total pressure of 2 atmospheres. That's another way of saying when will this number be 2 atmospheres or 202,000 Newton meters squared. So P sub P, by the way, your textbook maybe writes this as P total. So therefore, H must be the total pressure minus the pressure at the surface from the atmosphere itself divided by G times rho. Okay, so what we have here is 2 atmospheres minus 1 atmosphere divided by G times rho. Or in other words, 101,000 pascals divided by 9.8 Newton per kilogram times 1,000 of these kilogram per meter cubed. So now we plugged all these guys into a calculator. I'm not so great at actually dividing by 9.8. I can give you an approximate division of 9.8. If we do it the approximate way, then you have 10.1 meters. If we do it the not approximate way, let's see what we get. We have 101,000, dividing it by 9.8, dividing that by a further 1,000, we get 10.306. I've picked up an extra significant figure or two. If you want a good approximation, 10 meters of depth in freshwater gives you 1 atmosphere of additional pressure. And the approximation is even better, as it turns out, in salt water. Okay. Now we come to the last thing of the lecture, the Archimedes Principle and how it is applied. So Archimedes' Principle basically says that if you immerse an object in a fluid, then you will displace, if you totally immerse it, I should say, you will displace the object's volume in fluid, and that means that you will be getting a buoyant force upward on the object by the object's volume worth of fluid weight. So it's another way of saying this statement right here. This buoyant force that I've written up here, this is the equation form of Archimedes' Principle. Okay, so now let's apply this to two conditions of immersing an object or dropping an object into a fluid. And it looks like the hand is a little wobbly on my clock, but I have just enough time to explain it. Two conditions. Condition one, you have an object which is floating at the top of the fluid. Maybe your object looks something like this. Archimedes' Principle says that the weight of the object and the weight of the fluid displaced have to be equal, because the buoyant force must equal the weight of this object in order for the object to float. Okay, so in this case, we might write something like that. Basically, weight of the object and weight of fluid displaced are equal to each other. Condition two, object is totally immersed. In this case, volume of object and volume of fluid displaced have to be equal to each other. From that, you can figure out how much force you're getting on the object from the buoyant force. It should be the volume of the object times the density of the fluid times g. Right? So this right here, as stated, really is for an object which is totally immersed. If you want an object which is not totally immersed, then we might add to it something like a submersion fraction. So we could call that like an eta. So we've modified our equation slightly. Now it's correct, as is, for a single fluid at least. And what that last little addition lets us do is figure out if you have an object which is going to float, what fraction of it must be submerged and what fraction can be seen above the water's surface. So you have an object which is floating, some part of it's underwater, some part of it's above water. What is that fraction? Well, if it's floating, this right here holds true. This means that volume of the object times density of the object times g must be equal to the volume of the water displaced, which is just another way of saying the fraction of the object which is immersed in the water times the volume of the object times the density of the fluid times g. All right, so we want to solve for eta. Eta must be volume object, density object, g, divided by volume object, density fluid, g. So we can cancel some like terms, and we just get density of the object to density of the fluid. All right, and we're out of time on that note.